Hi, this is Roger from Kanka Labs, and today we talk about some unknown properties of inductors, aka coils. And as you can see here, with a radio reception coil, also called a spiderweb coil, you see directly connected to a square wave generator. And what do we get out of the single element inductor? Well, it behaves like a tank circuit, a parallel resonant tank circuit. So, and why this strange behavior comes from this single passive element as in the form of an inductor? That's what we talk about today. Make some experiments, make some calculations, and some explanations. What you have to watch out for when using inductors or coils in your circuit. So we'll simply start with the properties of an ideal inductor, which has no resistance and no parasitic elements. And I will use the European symbol of an inductor here. And as with a capacitor, an inductor does have an impedance, and you can look upon as impedance with the letter Z or Z as the resistance for AC voltages. And this resistance or impedance is not constant, but it varies linearly with the frequency. And the formula for an ideal inductor is quite simple. It's 2 times pi times the frequency times the inductivity. So that means if we plot the inductance Z versus the frequency F, we just get a straight line, which means the resistance for AC voltages increases linearly with frequency without any limit. That would be great for using an inductor as a filter, because the impedance becomes larger and larger the higher the frequency is, which means the current flowing through an inductor, for example, if you want to filter a power supply line, the higher the frequency, the greater the resistance, while for DC voltages, the resistance starts at 0 for an ideal inductor. Now, of course, there is nothing like an ideal inductor, so let's take a look at how a real inductor looks like. So a real inductor does not only consist of the inductor itself, but you have at least the copper resistance in series. But it's not only the copper resistance. This comes into play only for DC currents. When the frequency increases, there are additional losses. They come from things like the skin effect, proximity effect, from losses in the ferrite material where most inductors are wound on. And there is still something else, because if we take a look at how an inductor could look like this spiderweb coil, which of course is nothing else but an inductor, you can imagine that between each winding there is also a capacitance, even if it's small, but it adds up if you have many windings. And so we have a parasitic capacitance lying in parallel to the inductor and the parasitic losses in the series resistance. And now what we have is this forms nothing else but a tank circuit. In this case, a parallel tank circuit, because we have an inductor in parallel with the parasitic capacitance and the parasitic ohmic resistance. This determines the Q factor of the tank circuit. And if you have either watched part 1 and 2 of our video series about AM magnetic antenna, you will immediately recognize this as a damped tank circuit. So if you are lucky and you get an inductor from a quality company, you might get an extensive data sheet with graphs showing how the impedance here varies with frequency. And what we can see here at this inductor is, first of all, the impedance rises just as we would expect from an ideal inductor. It rises linearly with frequency. And although the axes here are both logarithmic, a linear rise in double logarithmic scale remains linear. But then we see the impedance peaks at some point and then it goes down again. So this is exactly what we expect from a tank circuit, a parallel tank circuit. The shape of how the impedance is going with frequency is exactly that way. And now we directly know that the parasitic elements are building a parallel tank circuit, and that's the reason for that a real inductor cannot filter frequencies above its so-called resonant frequency. That's where the peak is. The frequency where the peak is, which is of course different for different values and types of inductors. The filtering effect of an inductor for high frequency reaches a maximum at the resonant frequency, and then it goes down again. So you, with real inductors, you cannot filter out frequency which are very much above the resonant frequency. Now, there are even some suppliers which show you a little bit more extensive graphs about the behavior of an inductor, and I'll show you another one. And here we have really a lot of data. This is a Fastron inductor. We first of all see none of the values is constant. Even the inductivity is not constant. Here in this case it rises with frequency above a certain point. It remains constant up to a certain frequency and then it rises up. Very strange. The Q factor also is not constant. It also varies with frequency and of course again with the type of inductor and the value of the inductor. And here we again have the typical behavior of a tank circuit. Here the resonant curve is a little bit distorted because here are additional effects coming into play. But anyway, we see the typical shape of a resonant parallel tank circuit. And now here in the table for the data, we even can see the Q factor for the different values of this type of inductor. We get a measure for what's called SRF. This is the abbreviation for series resonant frequency. I don't know why it's called series resonant frequency, because we have a parallel tank circuit where inductance and capacitance are in parallel. So I think it should more precisely be called parallel resonant frequency, because perhaps one of you knows what's the reason why this is called series resonant frequency here. And we have the DC resistance, and remember the parasitic resistance here, it's only for DC voltages, it's the copper resistance, but for higher frequencies this resistance rises due to skin effect, proximity effect, and losses in the surrounding material, which most often is ferrite. But if we take a look at another kind of inductor, namely this spiderweb coil, here we don't have any ferrite material, but we have this plastic here where the coil is wound on. And here you have, instead of magnetic losses in ferrite material, here you have dielectric losses in the material of where the coil is wound on. Now, if we have, we are lucky and we have a quality supplier and you know which kind of inductance you have, you can get the data from the data sheet. But what do you do if you have an unknown inductance or inductivity? Is there an easy way to measure as well the series resonant frequency or parallel resonant frequency and the Q factor? Well, yes, there is, and therefore let's take a look again at what we saw at the beginning, how we build up our test setup to measure Q factor as well as series resonant frequency. Now, the basic setup looks like this. You take a simple square wave generator, and it mustn't be an expensive digital one. You can take any kind of, you can build up a TTL oscillator or anything like else. It should have an amplitude between 5 and 10 volts peak. Then you take a 10 megohm resistor. That's quite important to use the highest value resistor available. Then you connect this to your unknown inductance or your inductance with unknown properties. And we know that we here have the parasitic capacitance, and which is now difficult to put in the series resistance here. So that is our inductance with unknown properties L. The lower end we connect to ground, and then we take our digital oscilloscope, or it can also be an analog oscilloscope, no problem. And we should take the a probe with a 10-to-1 divider because of two reasons. You usually then also get 10 megohm input impedance, and that's quite important because even a very high impedance as well from the function generator and for the oscilloscope, it loads the tank circuit. And you might think, well, a few kilo ohms should be enough just not to load the tank circuit. No, that's not the case. Because if you have coils or inductors with a very high Q factor, then the so-called resonant resistance, which can be looked upon as the you can look upon a tank circuit as a voltage source with an internal resistance, which is called the resonant resistance or resonance resistance, which can go in the megohm range. And you just not to distort your measurement and to artificially lowering the Q factor, both resistance of the oscilloscope and from your square wave generator They should be as high as possible. Usually 10 megohms are sufficient. And of course the ground of the oscilloscope, all three grounds are connected, and that's the test setup. And to get a stable triggering, it's a nice feature just to trigger the oscilloscope with the square wave. And the frequency of the square wave is not very important. It should at least be 10 to 20 times lower than the expected resonant frequency. So it's enough to have something in the range of 1 kilohertz, because most resonant frequencies are in the range of megahertz. So 1 kilohertz square wave frequency gives you no problem. It could also be 100 hertz, it could be a few kilohertz, but don't go over a few kilohertz, because then you get other effects that you don't want to have. So very simple test setup. You only need a 10 megohm resistor, a TTL or square wave generator with an output voltage between 5 and 10 volts. It could be also a little bit higher. But 5 volt is absolutely sufficient, and you need an oscilloscope, no matter if analog or digital, with a 10:1 scope probe. And it's easiest just to trigger the oscilloscope with the square wave signals. And even the cheapest and oldest oscilloscope has an external trigger input, so that you can get a stable triggering automatically from the square wave generator. So that's how it looks like, very simple. And with this setup, we can, as you can see in a second, we can measure both the resonant frequency as well as the Q factor. So here we have an overview of the test setup in reality, just before we take a close-up of what's happening on the screen of the DSO. You can see I've put our Rigol function generator to output a 6 kilohertz square wave, and you can see the square wave here in blue. And at every pulse of the square wave, no matter if it's the falling edge or the rising edge, the tank circuit here, which consists only of this spiderweb wound coil, but with the parasitic resistance and parasitic capacitance, it is excited. Just turn down the y-axis. The tank circuit is excited at each edge of the square wave signal, and you can see beautifully the dampened oscillation here. And now we just to make some measurements, we will just take a close-up of the screen of the DSO. You can see here is the 10 megohm resistor, the outputs of the function generator, and the input of the oscilloscope here with the 10:1 probe. They are connected at one end of the coil, and the other ends, the ground leads are put together, and the signal is fed in via the 10 megohm resistor. So the test setup just exactly as I just showed you on paper as a schematic. And now let's take a closer look at the waveform here. So now I think you can see a little better what's happening on the display. And first of all, we'll increase the scale on the x-axis a little bit. And now you can see better the dampened oscillation. And the next step is we will fine adjust the height of the first peak, of the first cycle exactly to the upper end of the screen with the x-axis fine-tune. Okay, this should be enough. That's because the we do this because the first cycle after the tank circuit is excited, it determines the peak voltage, the starting voltage of the oscillation, and then we just start to count the number of cycles until the amplitude of the oscillation has died out to half of the first peak value. Let's get this in. And now it becomes a little bit difficult. I will do the counting for you. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, nearly exactly 10 cycles until the amplitude of the oscillation has dampened out from its peak value to half the peak value. And this number of counted cycles for the decay to half of the maximum amplitude, you take this number by 5 and you have the Q factor, which means if we count 10 cycles for the decay of the oscillation to half of its amplitude, then the Q factor at this frequency and with this coil is exactly 50. So we have determined our first value. Just let me repeat it. You just take the number of the cycles until the amplitude has decayed to half of its value, multiply it by 5, and that's the Q factor. So, and now to measure the resonant frequency, we simply turn on the cursors. Just take a look. Now we have cursors set to manual. We select the vertical cursors to measure simply the time difference of one cycle, and we have cursor A now activated and are moving cursor A here to where our signal crosses the 0 line. And now we change to cursor B, which is the dotted one, and we set it to where the cycle is full, which means 2 0 crossings later. So we have one sine wave here between the cursors. Now we get displayed the difference between cursor A and cursor B is 1.47 microseconds, and the oscilloscope is just so nice to take the reciprocal of that, and that is 680.3 kilohertz. So we have determined with one simple measurement as well the Q factor, in this case it's 50, and the resonant frequency, which here is 680.3 kilohertz. Now let out the 0.3, it's 680 kilohertz. So, and with these two values, we can do some math to determine the other factors of here this inductance that we used. But before that, there is still one question. We now have measured the Q factor and the resonant frequency only for the case of the resonant frequency itself. So we have one value of the Q factor, but we have seen beforehand that the Q factor of a real coil is not constant with frequency. So how could we determine the Q factor for other frequencies? So, quite simple. If we know that the resonant frequency of a tank circuit is determined by the inductance and the parallel capacitance, well, we simply can put another parallel capacitance. In this case, I've taken a variable capacitor and I connect it exactly at this moment, and you can see the frequency has gone up. And if I change the value, the frequency goes lower and lower. And so with just switching, connecting either a fixed or a variable capacitor in the right range to our coil, to our inductance, we can simply change the resonant frequency and measure now the Q factor, which surely has changed, but I won't repeat the measurement. Anyway, just by putting a capacitor in parallel to our coil, then we can determine the Q factor at any frequency we want. So that's the method of getting a whole set of values for the Q factor, because in some application it becomes quite important really to know the Q factor at one specific frequency, and that's the way you do it. And now let's go back to, well, not the blackboard, but a piece of paper, just to do some math to get out the parasitic values of our coil here. So let us for a second recap what we already have. We know that our real inductor does not only consist of its inductance L, but it has a series resistance where the ohmic losses and all other losses are put together. And we have a parallel capacitance, basically due to the winding capacitance, and this is as well parasitic as well as parallel. So that's how our inductor looks like. What we already have measured was the resonant frequency for our coil that we investigated. It was 680 kilohertz. We know the Q factor at this frequency, it was 50, but I know the inductance of the coil beforehand, and if you watched closely you could already read it. But if you have an unknown inductor, well, you somehow have to measure it, and you don't need an expensive LCR meter. You can also use these, one of these cheap so-called component testers. This is the one we have in our shop, which is an improved version of the Chinese one. I've already made a video about the improvements, and I've connected 2 of the 3 test leads with our no longer unknown, but let's suppose it's unknown coil, and let's see what it does measure. After a few seconds we get displayed even the parasitic DC resistance. Remember, this is, although it is measured here at 546 kilohertz, well, let's take this as the parasitic resistance, and the inductance is 2.0 millihenries. You can see printed here it's 1.9 millihenries. That was determined with an more accurate LCR meter, but anyway, the precision is in the range of a few percent, and that's quite good. So let's round this up to 2.0 millihenries. Oops. And the series resistance here is set as 32.4 ohms. Let's compare this with the DC resistance, if this is really the parasitic resistance or the series resistance at the measurement frequency here. So I'll just in a second. Let's see again if we get the same results. Yeah, the measurement frequency is set to be 544 kilohertz. Just ignore the Q factor here. But let's compare this with the DC resistance. If we get the same result, what I'm expecting, we get a lower DC resistance. So I've connected my multimeter here, which directly plugs into these 4 millimeter banana plugs, and we get a DC resistance of 30.5 ohm. So I'm quite sure that the component tester did not measure the series resistance for the frequency it displayed, but it did in fact measure the DC resistance, the pure copper resistance, which is here quite high because the coil is made out of thin Litz wire, and you can see there are I think a few hundred turns. So these are the things we already know, and what especially is missing is the parallel capacitance, and I'll show you in a second how we can calculate this. So even if you're not an electrical engineer, you might at some point have heard that the resonant frequency of a tank circuit is 1 over 2 pi times the square root of the inductance L times the capacitance C. And C is now what we are searching for. Now we just change the formula to give us C. In this case, it's the parallel as well as parasitic capacitance, and that is 1 over 2 pi times the resonant frequency, which we already know, and that is squared, and then times L. And this gives us the unknown parallel capacitance. And if we put that into a calculator with the values that we already have, we take 2 times pi times our resonant frequency, 680 kilohertz. We square this up, multiply it by the measured inductance, 2 millihenry. And then we take the reciprocal of that, and we get 27.4 picofarad. So in our, where is it? For this coil with rounded up 2 millihenries, a Q factor of 50, a resonant frequency of 600 kilohertz, we simply get the unknown parallel or parasitic capacitance of 27.4 picofarad. And there is also a formula to get the parasitic series resistance, in that case at the resonant frequency. But I won't go too deep into theory. This is something that will be discussed in part 3 of our video series about resonant magnetic antennas, because this is so important that, and it's there are many factors I already mentioned. It's not only the copper resistance. The copper resistance is only for the DC resistance important. But the series resistance goes up with frequency due to many effects: skin effect, proximity effect, and losses in the material of the coil, where the coil is wound on. Either if it's a ferrite, it are magnetic losses, or if it's, as here, it's plastic, then it are so-called dielectric losses. And there is still a fifth point where losses can appear. So that is just quite too much for this video. Let's be that sufficient for today. We have seen an easy method to measure with one measurement Q factor, or with one test setup, the Q factor and the resonant frequency of a single coil without any additional parallel capacitor, because the internal parasitic capacitance comes into play. If we want to measure the Q factor and resonant frequency at different frequencies, we just take an additional external capacitor in parallel, and thereby we can of course only lower the frequency with that. And then with what's in Germany called Thomson's formula of oscillation, we can just calculate the missing parallel resistance, and if we don't know beforehand the inductance of an unknown inductor, we just take either an expensive LCR meter or just a simple component tester from China, here in an improved version, improved firmware and improved accuracy, and with some little nice test clips here. And well, that was it for today. Perhaps something new for you to know about inductors and coils, which are nothing else but inductors, about their parasitic behavior, and that nothing in the real world is perfect. So, thanks for watching. If you liked it, please give it a big thumbs up. And that was it for today. Thanks for watching. Until next time, bye from Roger, bye from Kanka Labs.